What's up, Mindsetters? My name is Megan, and welcome grade 11s to today's Physical Sciences show. Today, we have a special revision lesson on forces, especially prepared for you. We'll be selecting highlights from the lessons shown early in the term to help you revise for your end-of-term tests. You can download the notes for today's show on learnextra.co.za/live.
Let's get on to what happens when we can use a calculator, which I have to be honest, I prefer. I don't like scale diagrams. I don't have enough patience. So, says to us, James exerts a force of 12 newtons on a box placed on a horizontal frictionless surface. Okay, so let's draw a picture of what's going on because that always helps. So, James, we have a box. He exerts a force of 12 newtons. Let's just say he's going this way. There's my 12 newtons. This diagram at the moment is for me. Okay, this is for me to know what's going on. And at the same time, Precious, oops, should be capital letter, exerts a force of 5 newtons at an angle of 90 degrees to the box. So Precious exerts a force of 90 degrees. So now it doesn't tell you whether the force is up or down. Okay, so let's say she pushes upwards. Okay, let's just make it a bit easier. So now she's pushing on the box at 90 degrees with 5 newtons. So it's at 90 degrees. So that's a force diagram, basically. If we had to draw this as a free body diagram, just including the forces that Precious and James exerting on the box. So what we have there is James is going in that direction, and Precious is going in that direction. So there's my 5 newtons. Let's make it so that you can read it. 5 newtons, and there's my 12 newtons. And we go, okay, big NB in the way this is asked. It says to us, calculate the magnitude and direction of the resultant force. Guys, please be careful. In your exams, particularly at the end of next year in grade 12, if they say to you calculate and you do a scale diagram, you don't get any marks for that because you haven't answered the question using the method they told you to. Calculate means calculation. Okay? If they said determine the magnitude and direction, then it doesn't matter. You can do it however you like. We're going to do it the way they want, which is by calculation. Okay? So, that means we need a diagram that we can use. So we're going to change this into a vector diagram. It's not a scale vector diagram, but it's one we can use, and we're going to draw it head to tail. So all of this stuff in green was for me. Okay, now we start. Okay, now I'm doing my calculation, and we say, fine, James went off in that direction, so let's call this the force of James. I've only got James and Precious. I'm going to use a J and a B, and James had a force of 12 newtons. Precious went up here. Let's call it the force of Precious, which is 5 newtons. So my resultant is from the beginning of James to the end of Precious. Still do this with the ruler so it looks nice and neat. And there's my resultant. Okay? Now we look at this and we go, we can do this because that was at 90 degrees. You know this. You've done this since last year. You did trigonometry. You did Pythagoras in grade 10. So we go, yay, easy. Let's ignore the angle for now because we are going to need to know what this angle is. Let's work out FR. And we go, well, it's a right angle triangle. It's a really badly drawn right angle triangle, but it's a right angle triangle. And we're actually looking for the hypotenuse. So we remember Pythagoras' theorem says to us that the square of the hypotenuse is equal to the sum of the square of the opposite two sides, something to that effect. Okay, it's been a while since I taught maths, which means, please watch how I set it out, grade 11s. This is important. My hypotenuse, which is FR, is equal to James's force squared plus Precious's force squared. Okay, that means we've got 12 squared plus 5 squared. We take out our calculators, okay? That gives me 144 plus 25. So the square of the resultant force is 169. I don't want the square. I need to square root it. So we say, okay, that means that my resultant force is 13 newtons. But I haven't finished. Because the question was magnitude, done, and direction. Okay, not using a protractor. Go back to our diagram. Okay, so we know that this is now 13 newtons. Grade 11s, you can now use any of your trig functions, sine, cos, or tan. I'm going to say to you, as a tip, don't use sine or cos, because sine or cos require you to use the hypotenuse, the 13 that you've just worked out. If your 13 is wrong, which we know it's not, but if it's wrong, then you're going to get the angle wrong too. And carry down errors are horrible. You don't want to have a carry down error. So let's not have a carry down error, okay? So let's use tan. Watch again, and now we got to remember, tan is opposite over hypotenuse. So tan means, tan theta for this one is going to be the opposite side, which is precious, divided by James's force. Please be careful about using your maths lingo here and making it x over y or y over x or whatever it is, simply because there is no x or y on your diagram, and sometimes you guys forget to put a diagram because you drew it on your question paper, and then we don't know what you're referring to, and then we can't give you marks if you go wrong. Okay, so that means it's going to be tan theta equals 5 divided by 12. Now, we need theta. Now, I want to show you how to do this on your calculator just in case you've forgotten. And we can do this in one step. So we do second function tan, because we're looking for the angle. Okay, so we arc tanning. Then we're going to go 5 divided by 12, and close your brackets, please. Okay, so the calculator knows that was the one that we wanted. And we go equal to, and we get 22,62 degrees. Remember, we've got to round it off to 2 decimal places no matter what. So 22,62. So this is, let's do one more step. So theta equals 22, what was it? 62, hey? There we go. 62 degrees. Okay? I know the magnitude, I know the direction, but I have to put it together. These are all separate, and they're all nice calculations. So what does that mean? So then we go, therefore, my resultant force is 13 newtons at 22,62 degrees from the force of J. Okay? Or because James was horizontal, you could have said it's 13 degrees, at 22,6 degrees from the horizontal. Okay? But it's from James. This is where the 22,62 degrees goes in. Okay? So remember, force is a vector, which means when I want the whole force, I've got to give the magnitude and direction as one thing, not in two separate answers. So we write it out. It's almost like answering a word sum in maths where you have to answer a word sum with a sentence. Same thing.
Let's go to a short break now. Remember, if you are struggling and you need help, remember to post your comments and questions on our Facebook page, facebook.com/LearnExtra, or on Twitter @LearnExtra. Don't go away. We'll be right back. Welcome back, guys. let's get into some more revision.
We're going to do a bit of a demonstration, and I'm going to talk you through what we're going to do. And this could also be a really nice way for you to calculate the coefficient of friction. Okay, this is a way we can calculate things. Now, what are we going to do? Well, the question that we want answered today is what happens to the maximum kinetic friction when we change the type of surface on a slope if the object stays the same? That's my investigative question, okay? And I want you to see something here. This is really important because in your exams and stuff, you're going to get often asked to write an investigative question. First rule is it mustn't be a question that you can answer with a yes or a no. So I couldn't ask, does the type of surface affect friction? Yes, that would be a yes or no answer. So that's not a good investigative question at all. But what happens says, okay, we're looking for a relationship. Sometimes that's mathematical, sometimes it's not, okay? So what happens? Then we've got to have our variable. So we're saying what happens when to the maximum static friction, so that's what we're going to be measuring, so that's my dependent variable. When we change the type of surface, independent, I'm controlling it, when the object stays the same, control variable, okay? Relationship, independent variable, dependent variable, control variable, okay? Simple, simple, simple demonstration, which we're going to get Ty to help me in a second. Awesome. We're gonna place a box. We've actually got a mass piece from a trolley onto a nice wooden plank. Then we're going to lift the plank to just when my mass piece starts to move. That means that I've overcome friction, okay? We lift it up, and when it starts to move, the force of gravity pulling it down is enough, okay? So friction is no longer holding it from moving, okay? Then we're going to measure the height of the slope. We're going to mark it on a meter rule, and we're going to repeat it, but we're going to put different stuff on it. So we've got carpet, we've got a rubber mat, we've got a towel, we even got the other side, it's got a nice shiny mirror on it, so we've got smooth surfaces. And then, once we get an idea that we're going to see if you can describe the relationship between the types of surfaces and the friction. So in other words, what we're looking at is, do you think, so this is what you need to think about as we do this, do you think smooth surfaces have more friction or less friction? Do you think the roughness of the surface is important? Will that make it have greater friction, less friction? Remember, I'm keeping the object the same, so weight is not an issue, okay? And then we'll see from there. So, Ty, my friend.
Yes?
You're going to need to come over here. So we're going to go and investigate quickly.
Alrighty.
Okay, so what we have here, it's very simple. You can stand over here. Okay. And we've got all my goodies. You see this?
Awesome.
Yep, there we go. And we have a mass piece. It's about 1 kilogram in weight, so it's just nice and heavy. We don't want something too light, because if it's too light, well, then it just
kind of defeats the whole point.
A little mass doesn't play that much of a role as such, but this is got nice weight, so you know it's not gonna, you're not gonna lift it like this much and it's gonna start moving. So we have our meter rules. Now these we're just gonna mark them. I'm not too concerned. I've got a whole bunch of pens. We're gonna do different colors. So we're gonna see how ambidextrous you are right now.
Alrighty.
Okay, so we have our, now don't lift it too quickly, otherwise we're going to defeat the object. So I'm going to put it there, okay, and Ty, if I need you to lift it up for me.
Okay.
Okay, it's not moving, lots and lots of static, keep lifting. It could take a while, keep lifting,
okay.
keep lifting, keep lifting. Ooh, okay, there we go. Did you see, okay, let's try that again so we can sort of, you see that it moves. Not moving, okay, then Ty lifts it. Okay, and now watch. It starts almost. There we go. Wow. Okay, why did you put it down, Ty? I need to measure the height.
It's all right. There it is.
Really?
I remember where my arms went.
Some assistance. Okay, but watch, we can see it anyway because we can put that on and it's going to move. So it's fine. It's roughness. Now remember, every time, this is wood, so that changes. Okay, so what we're going to do is over here, and let's mark it Okay, so. Oh, wow, that was actually pretty cool. We got it 23. I did mark it the wrong way around, so it's actually 27. Don't tell anyone. Should have marked it this way. Anyway, we'll just keep it this way anyway. So this is just the wood. Now, let's think about this. Instead of the wood, okay, you can put it flat again.
Okay.
I'm going to use, this is like the rubber mat we put in a car, okay? And we're going to use this side. Now, why would we put, Ty, you can answer this for me. Why would we have this in the car? What's its purpose besides keeping the car clean?
Well, that's also for our shoes not to slip.
Right, shoes not to slip. So we would think that it would need lots of friction.
Yes.
Perhaps, because we don't want it, especially us girls, when there's like
And there's heels involved, and there's sandals. It gets
messy, yeah. So we're going to do the same thing, okay? So I'm going to put this on here. So Ty, go for it. I think we know what we're trying to do this time. And we'll see if we can get it any different. It already looks like it's going differently.
Yeah.
Okay. So
Okay,
we're
going
going to
up.
see there. Ooh.
There.
There we go. Now, I want you to note this. Keep it there. Sorry, it's just your workout for the day.
It's all
Can you
good.
see it's moving very, very slightly? But that's exactly what we want. We don't want a rubber mat that's so smooth, because some rubber mats are still smooth, that this just slides down. Because if you make a little bit higher, there we go. This is actually, there we go. That's what we wanted, okay? So, I'm now going to use the green pen. We're actually going to lift it. See, I'm still going to do the same around, so it's okay.
Might as well.
Might as well. And here we go. So, actually, that made a difference. If we can see, you can put it down again. That made a difference in height of 1, 2, 3, 4, almost 5 centimeters. That's a lot. That's a big angle, okay? So the rubber mat's got lots of friction. Let's try the carpet. Okay? So, let's try the carpet. We all love these things. Okay?
Yes.
And we feel it. The carpet's quite rough. This is nice
Especially
industrial.
barefoot. They're awesome.
Oh yeah, I actually quite like walking on a carpet like this one's barefoot. Anyway, moving on. But it's quite rough. This is a hard carpet. This is industrial carpet. This is what most industry have, because it's
And
nice
offices
and offices and stuff. And we don't want it to have a lot of slip, so we expect it to have a lot of grip. It's rough. So should we see?
Let's go.
Okay, there we go. Off we go. Let's see how we do, because we can make a prediction. I'm not going to make one for you. I'm just not sure. I mean, ooh, look at that. It's trying.
Oh, there.
But now watch when this goes.
There
Look
we
how
go.
much faster it goes. That was brilliant, okay? Because with the rubber, it started to go, and then it took a long time.
But
So
it
it still
inched
had,
down,
had a lot of grip, which means it actually has a lot of kinetic friction. This, which we'll explain in a second. So let's do it here. And there it is. And, oh, look at that. So this was the wood, that was the rubber, and then this blue mark over here is the carpet. So it's less than the rubber, which makes sense, I think, because it slid nice and easily down there once it started moving. Okay, so that was pretty cool. I like that. Okay, we have 2 more surfaces to go. Okay, now we have a towel. Oh, looks like, there we go. So now we've got a towel. And towels, we like towels after a bath. And this one's going to be a hard prediction, because for us, as we feel, it actually feels quite rough, okay? Because of the pile on it and stuff. But it's definitely not as rough as the carpet. So let's see where it goes, okay? So there we go. Let's see. Okay. Going up. Ooh, look how low that is. And look how nicely it slides.
Slid all the way.
Very nice. Now that's actually quite important. So let's see. Ooh, wow, it's very low. There we go. Look at that.
Way lower.
And compared to, now this is the low, so even compared to just the plain wood, which in our natural, sometimes we sort of go, that doesn't make sense, because this feels rougher, but it's the type of material. The wood, even though we can't see it, has lots of rough areas in it, and that's what gives it its friction. We've got 1 more surface to try. So Ty, you're almost done with your weightlifting for the day.
It's all
So
good with me.
let's turn this over, because what we have here is a mirror, okay? Now, the only reason why we're using the mirror is it's good enough for glass. So this is the smoothest we've had out of all of them. So we should get it to slide down quite nicely, hopefully without any scratching noises. So,
Or breaking it and 7
Oh,
years bad luck.
yeah, breaking it would be bad. Yeah. Anyway, so go for it, Ty. Let's see how we do without messing up the lights in the studio. Now, this is interesting.
That is.
Look
There
at
we
that.
go.
But look at the difference. It goes down. It's nice, but I wanted to show you again that it's starting to move. And it's okay. I got told that wouldn't be a problem. Okay, let's not do it in blue because I think we'll miss where it is. And then we'll do it here. Ooh. There we go. So, it's my last red one. Thanks, Ty.
It's a pleasure. So can I leave now?
You can go back to your post and talk to our mindsetters. Let me just do this without me losing my glasses. Okay, that's when there's no friction between the glasses
face
and your
and the
face.
stuff then.
Okay, so if you look here, that's the mirror, the one at the bottom here. That was the towel. Now, instinctively, I actually really did think the mirror would be lower. But it's all to do with the surface, okay? So let's go back to the board because we have a couple of questions that we need to answer about what we just did, okay? So we're going to go back to the board. And the whole point of this was we were asking, can we describe the relationship between the type of surface and the amount of friction experienced? Well, the surface does affect how much friction you get. And in fact, the rougher the surface, the more friction we experience, though we have to be careful with that. Because the rubber mat appears quite smooth. So if we feel it with our hands, it feels smooth. So that's a bit of a difficult description because even between the towel and the mirror, which is those two at the bottom, which are so close to my hand, the towel feels a little rougher. So rough is a difficult one to put into words. So what we're actually looking for is the microscopic, is what's happening microscopically. Because in any surface, we can actually draw it as being, well, any surface microscopically has bits coming up and down and in and out, and they're not actually smooth. We can't see that. So when we put another surface on top of it, so this is one object, and then we put another surface on top of it that's also got all these little ridges and things on it. When these two parts of the surfaces interact with each other, that's what causes the friction, okay? But from my meter rule, though I did put it upside down, and it's not a problem, though. My challenge to you is to do this with the meter rule the right way round, extend your maths a little bit, and see if you can work out what the coefficient is, because this is exactly how you can do it, okay? Because we can get this, so it makes lots of sense. With the green was the rubber, then we had the carpet, this was my wood, this was the glass, and then there was my towel. So I can already see the height makes is very, very important, okay? So the relationship between the type of surface and the amount of friction experienced by the box is that the rougher the surface, the greater the amount of friction. So, let's look at some questions. So the first one we're going to look at is, it says to us that a 50-kilogram crate is placed on a slope that makes an angle of 30 degrees with the horizontal. Okay? The box does not slide down the slope. Calculate the magnitude and direction of the frictional force and the normal force. So now, grade 11s, draw a picture. Because drawing a picture always makes life easier. So we have a slope. Whether you draw it up to the right, up to the left, doesn't matter. It really is your choice. I tend to draw it up to the left because I don't know, I just do. So There's my slope. I need to know where my angle, where my horizontal is. So there's the horizontal. And we have an object on my slope. No, that's not what I wanted. We'll draw a box. So there's my box. And they said that that was 30 degrees. Okay? Then they said to us that the object has a mass of 50 kilograms. That's quite important, so we'll put that in a second. So we're just going to make a note for ourselves that it was 50 kilograms. Let's just double check that I'm right. Yep, 50 kilograms. Now, they want us to calculate the normal force, and they want us to calculate the frictional force. So we say, okay, let's start with gravity, straight down. That's okay. We can calculate Fg, not a problem. In fact, we can do that in a second. So that's weight, Fg. Okay, cool. Friction is going to act up my slope. Okay, good. And my normal is going to act that way. So this is friction, and it's going to be static friction because it's not moving. And that's my normal force. Now we've got to say to ourselves, okay, now we've got to find a way to relate this to my weight, because weight is acting straight down, only force acting on the object, but weight is now almost like when I'm pulling something at an angle, or I'm pushing a wheelbarrow, or pushing a shopping trolley, or something like that. The force is at an angle to the slope. So we're going to do a little bit of geometry here, and we go, well, actually, and I'm going to do it as a dotted line. There's a component of weight that does that, goes straight down, okay? Let's just make it so it's in line with the front of the, there we go. So part of my weight is I can now split it into two forces that together do the same thing. One of them acts straight down like that, and can you see by putting this one down here, it's actually in the same plane as my normal force. Now I know they're not exactly 180 degrees from each other because I'm drawing it freehand, but they at 180. So we're going, okay, this works for us. Then if we now draw another line at 90 degrees, right angle triangle, to this, because to my perpendicular component, I get this, okay? And that's, yeah, that'll do. Okay, and this angle is 90 degrees. Now you're saying to yourself, but Tracy, why did you choose 90 degrees? Because the normal and my frictional force are also at 90 degrees to each other. So can you see what I've done? This is the this force that's coming down the slope this way is actually the force that's pulling my object down. This slope that's going perpendicular is actually the force that my normal force is going to be. So we go, okay, that's cool, we can do this, but I need more information. This angle here is 30 degrees. Now, we don't have the time, unfortunately, for me to show you the maths, but you're going to have to believe me on this, okay? Because the triangle that I formed here, oops, without me doing extra lines, the triangle that I formed here is a similar triangle to the one with the slope, okay? What do we call all these nice new lines I've put in here? This one is FG perpendicular, and we use the perpendicular sign from maths, and this one is FG parallel, and we use the parallel sign for maths. So what am I saying to you? Your frictional force is equal to my parallel gravitational force, and my normal force is equal to my perpendicular component of my gravitational force. That's perfect. How do I know that they're equal? Because my object is stationary. No acceleration, it's not moving. That's enough information for me. So now we've got to decide how we can work this out. Okay, we're going to use some trick here, and we're going to go, fine. We are really only going to use sine, cos, and tan, so I want to quickly remind you that sine theta is opposite over hypotenuse. Okay, if you've learned it x and y's, I'm sorry, this is the best way to remember it for this. And cos theta is adjacent over hypotenuse. So if I'm looking at, I want FG perpendicular, sorry, is adjacent to my angle. So if I go cos theta, it's going to be equal to FG perpendicular divided by FG, which means that FG perpendicular is FG cos theta. And we remember that Fg is mass times gravity, and that means we're going to take 50. I'll write it here as well. So it's mg cos theta, and we go fine. We know m is 50. We know g is 9,8, not 10. And cos is 30 degrees. And I worked this out earlier, and I got 424,35. Okay? So therefore, my normal force is 424,35 newtons. Okay? We're not done yet though, because that's just part one of the parts. Now we do the same for my parallel. My parallel is opposite. So now I'm going to use sine. So now watch. If I go sine theta, it's my opposite side divided by my hypotenuse. So it's FG parallel divided by FG, which means sine 30 degrees. Oh, sorry. Let me just go back here. Sine, let's do here. So that means, let me make sense of this, that FG parallel is FG sine theta. So it's my weight times the sine of my angle, and my weight is m times g. Okay, so now we're going to go 50 times 9,8 times sine 30. Okay, and 50 times 9,8 times sine 30 is 245 newtons. So that means that my static friction, which is what I wanted, which we already stated is equal to my my parallel, is 245 newtons. Okay.
Let's go to a short break now. Remember, if you are struggling and you need help, remember to post your comments and questions on our Facebook page, facebook.com/LearnExtra, or on Twitter @LearnExtra. Don't go away. We'll be right back. Welcome back, guys. Let's get into some more revision. Over to you.
What I want you to do is you're going to follow me over here. We're going to go to what is known as a force board. So what I've got set up here with all my toys and stuff is a force board. Now I'm hoping some of you would have seen this. Sorry, I just need to put all my nonsense away. Okay. Now basically what this force board does for us, grade 11s, is it gives us an opportunity to set up a system where now I have 3 forces, and we're using mass pieces. These are just 100-gram mass pieces, and I've just weighted this one a little bit more. In fact, this is 150. And with using our pulley systems, they're not 100% frictionless, because these are actually quite old, but they still work, so we're okay with that. They can freely flow, they move freely, which is what we like. Okay, so they move quite freely, and we've set up a system where we have 3 forces, and this is the sort of system you get when you're hanging a picture on a wall. Okay, the picture hangs. You would have your hook over here, or and then you would hang your picture. This is where the picture is, and this represents the wires that come from the back of the picture. Okay, to hang it on a wall. We look at this and we go, okay, this is nice. What does that mean? Well, if you look at the system, as it stands, besides the fact that it's swinging, because I've been messing around with it, can you see that the forces, none of them are actually moving in any direction? So they're not moving towards this force. If I add to this, if I increase the force on it, then I can get it into a different position. They're not moving over here, okay? This one's also not moving. And in fact, if I pull that one down and then let it go, it'll go right back to the position it was in just now, okay? This is what we call the equilibrium position, because at this position, the system isn't moving anymore. All of this is the system. Now, how does that help us? Because now we're saying to ourselves, okay, that's great, nice for you. This now helps us when it comes to equilibrium. There's two types of equilibrium, grade 11s, and this is very important. We get static equilibrium, which is what this system is, okay? It's static because there's no movement. Remember you did static electricity in grade 10? Static electricity was when we studied charges that weren't moving, not moving. Then we get dynamic equilibrium. Dynamic equilibrium means that we have motion, but the motion results in constant velocity. There's got to be something that's the same. When we're looking at forces, and in grade 11 we're specifically looking at forces in equilibrium, equilibrium is equilibrium. Whether it's static or dynamic doesn't matter. So this static equilibrium is going to help us decide how we know that a system is in equilibrium. What is the point of it being in equilibrium? How do we find that out, okay? Now that means I've got to take the situation I have here and draw a force diagram. This might be new for some of you because we're going to draw an accurate force diagram with 3 forces, okay? A couple of weeks ago we started looking at investigating forces. We said we could do it head to tail. We've sort of mentioned components in the middle. We're now going to do this accurately. So we're going to take a pen, and error parallax becomes a bit of a problem, okay? So you're going to have to just trust me on this one. I don't want you to see the back of my head. What I would normally do, I obviously can't do it because I'll be in the way of the camera, is I would stand right in front of this, okay, so that I'm eye level with it, and I would measure my dots, okay? Now, you would use a pencil. Pencil's nice thin. Obviously, a pencil would be stupid because you won't see it.
You won't see it at
So
all.
we have my permanent marker, and what I'm going to do is I'm actually going to use the shadow lines, okay? You're going to have to trust me on this one. The shadow lines, because the lights are all the same for all 3, my shadow lines work. You can also do it so that if you hold it flat, you can draw onto your string, but then it gets all complicated and stuff. So what we're going to do, and we're going to hopefully get it to stop moving, because it really is having a nice day today. So we need 2 dots, because remember, we need to be able to draw a straight line. So I'm going to put a dot there. Ooh, when it stops. Oh, maybe it's my fault that it's moving still. Okay. I think there's aircon in the studio, so it's like there's a breeze. Okay, and there's the other one. That, when we draw the line together, is going to represent that force. Here's my other one. Okay, there's my 2 dots. And now we're going to do it for the one at the bottom. Okay, there we go. Okay. Now we need to quickly just make a decision, because what we have here is we have the system goes up and down, and let's do another pen. And we do this because we want to make sure. This is 100 grams, okay? Ooh. Okay, and as you can see, I can write just as well on paper as I do on the board. It's just as scary.
Nice and neat.
Yeah. And we'll keep telling ourselves that, won't
Yeah,
we?
we will
Okay.
keep telling ourselves that.
This is 150 grams, okay? This is just to remember. Now I'm going to ask you a question, which I know you'll all be screaming at the TV. Which way does gravity act? And you're all screaming at me because we remember this, it acts down. So this force is actually acting in that direction. This one's acting down. And that one's acting down. Don't think I've lost any of you yet. But this string goes all the way over here. So, in fact, when I pull this way, my object moves up, okay? So that means this force is actually in that direction, okay? And this one is in that direction. I need the direction, because without the direction, I don't have a force. Remember, force is a vector. Vectors have both sides and direction. Then, we go, okay, we're not doing too badly. What we can do from here is we take, now you would use a smaller ruler, obviously, but we've got a nice big ruler. Okay, and we're now going to draw in all our dots. I really am making Wilson's life very difficult. I'm sorry, Wilson. There we go. So that's my downward force. Okay, I'm going to do the one over here. Or not, ooh, no. Okay, my ruler's actually
I think your ruler's a bit too big.
just a little. Hey? Okay, what we're going to do is this. No, we can sort this. Don't stress. Okay. See, I'm a science teacher. I can make a plan. So let's do that. In fact, this is perfect. So we take this off. Okay. Hopefully, I haven't made any mistakes because I'm not going to put it back on in the same place again. And we go here. Okay, and you would hopefully do this a little bit more accurately than I am. Now, I know that I've got my diagram correct, grade 11s, because can you see they all meet in the middle? If my pulleys were still on, you would have seen it matches exactly. Now we've got to say to ourselves, okay, this is now starting to look like something you've seen. This is now starting to look like a problem you've seen because we have an object. It could be anything, okay, where the knots were. So this part here could represent any object that we had, a tree trunk, a person, whatever the case may be. And now we have three forces acting on it, going in that direction, and going down. So before we can do anything else with this, we've now got to get some important information because I'm drawing a force diagram. I can't draw a force diagram with masses, but I can draw a force diagram if I knew their weight. So we've got to remind ourselves, okay, first of all, that there's 1,000 kilograms, oh, not 1,000 kilograms in a gram. That's ridiculous.
I don't think that's the way it works.
It's not that way
Tracy.
around, hey?
No.
What do you think, Pumi?
Nah,
I don't think so either, hey? No, I agree. Yes, maybe Pumi should be teaching this because
Maybe,
apparently
I
I've
think
forgotten everything. Anyway,
I'd love to try.
there's 1,000 grams in a kilogram. So this is 0.1 kilograms. Mass is, weight is worked out by mass times gravity. Gravity is 9.8, which means my force here, and I'm just going to show you where I get it from, guys, is 0.1 times 9.8. So that's 0.98 newtons, okay? Which also means if this was 100 grams, this one's also 0.98. And you're going to have to believe me on this one because I worked it out earlier because this was 150 grams. This is 1.47 newtons. Okay, we're doing okay so far. We've got three forces. We're doing great. And now we've got to say to ourselves, all right, when we have these sort of things before, we got to say it's a vector. Great. Vector means magnitude, got that. Direction, half got direction. Because what I don't have here yet is angles, okay? So we go and we find our protractor, which I've put, excuse me. Okay, protractor ended up in the bag on the floor somewhere over here. Sorry, bag of tricks. You see, all teachers have these moments.
I know, right?
Hey, we do.
Guys, I have to encourage you, please go get a protractor like this one. That's clear, okay? If Wilson can focus on it for me, it's clear on the inside. That's so important. I know it's really hard to find these. Also, please don't get a 360 one because generally they're too big. I really would like you to get one where you can see all the little lines in the middle here. It makes life a lot easier. Those of you that do geography, I think you have anyway. Those who do engineering, graphics, and design, I think you would have. But please go and invest in one, and you are going to use it lots. Because what we're going to do with this one is we would now take it, put it onto my diagram, and we would measure this angle. Now, I'm not going to measure this one because it's actually worked out to be slightly different than the one I worked out at home. Also, my only issue with what I've drawn here is my pen is very thick, okay? And having thick lines, I know you go, oh, what difference does it make? Makes a huge difference when you're doing accurate diagrams, okay? So at home, you would do this using a very thin pencil. Here we go. Here's the question. It says, 3 forces act on a point O, which is actually in the middle. They're in equilibrium. Yay, we like that. Calculate. First question. Calculate the vertical components of the 60 Newton force and the 40 Newton force. Brilliant. So we say, okay, the 60 Newton force, so I'm starting with that one. 60 Newton force, the component for vertical. So vertical means I'm doing this component. Okay, and everything I draw into my diagram, I put onto my question, is F, no, it's opposite, so it's F sine theta. They're nice, they used special angles. You're going to get special angles quite often. I really hope you guys know your special angles. If you haven't, don't worry. It's why you have a calculator, okay? So please don't stress about it, and I have actually worked this out beforehand. So we've got 60 sine 45, and we get 42,43 newtons, okay? So the 60 newtons pulling up by 42,43. They wanted me to do the same with the 40 newton. Now, I know I'm doing it on the board on 2 different halves, but grade 11s, when you lay this out, can you see I'm labeling it? I'm saying this is the 60 newton, this is the 40 newton. Make sure your teacher knows which one you're working with, okay? Same thing, Fy is going to be F sine theta. In this case, it was 40 newtons, and sine 30, we like it, it's a nice special angle, gives me 20. Go, that's nice. What was the point? Well, look at the next part of the question, okay, which I've lost. Okay. Yes, no, the second part of the question didn't come out. The next part of the question actually says, now calculate W. And now you're going, excuse me? I want W. My system is equilibrium. We just did that if it's in equilibrium, horizontal components cancel each other out, vertical components cancel each other out. Other way around, horizontal, vertical. We've just calculated the vertical components of those two. Now, in order to cancel those two out, so now we say, okay, fine. We want W. My resultant of Y must be equal to 0, and it's going to be equal to W, because that's what they called the force, plus the horizontal from vertical from the 60, plus the vertical from the 40. I'm going to make down positive because I want to make my life easier. Together, this must be equal to 0. I want W. This is minus 42,43. This will be minus 20 because they go in the opposite direction, and I'm running out of time. When I take those over, it gives me 62, not 60, because I can't add. That's why you use a calculator, grade 11s.
Luckily, we have calculators, hey, Tracy?
Oh, man.
What would the world be without a calculator?
My brain would be dead. Anyway, so, guys, 62,43 because they must be equal, and I have run out of time. I hope this helped. I know I went quickly.
Well, guys, we've come to the end of today's show. Thanks for joining me. Remember to visit our website, learnextra.co.za/live to get the notes and to watch the videos. And if you are stuck and you have any questions, send an email to helpdesk@learnextra.co.za and we will help you. Also, guys, we are dedicating the month of March to Library Month. Join us as we discuss some great books and some exciting competitions on the way. Goodbye.